Sorry for delay.
Okay, can I start? Anytime? Okay. Hello, everybody. Thanks for joining. My talk is AUTOREV, a framework for automatic firmware reverse engineering. So I'm working as open source firmware developer at 9 Elements, and we wrote this framework just for fun and not for profit. It's open source, available on GitHub since yesterday. It's written in Golang, and it allows to do black box testing of firmware. It does abstract syntax tree generation and is then able to generate C code out of that. The whole thing is backed by MySQL database, and I'm going to explain all the details in the next few slides. So what's boot firmware? You all might know that's the most privileged code running on your machine. When you press the power button, it does all the hardware initialization. For example, that's core boot or UEFI. And it usually loads the bootloader from disk, like grub. And then the bootloader loads your operating system. And in this talk, I'm going to focus on the firmware part only, ignoring any later stages. If we look at core boot, it's written in assembly and C code and divided into multiple stages. And each stage loads the next stage. And every stage has a specific hardware initialization. Let me show you. If you press the power button and you see here over time, first of all is the boot block written in assembly, which loads the ROM stage that does the DRAM in it. And once the DRAM is available, we can initialize other devices like PCI, PCI Express, and so on. And after that, the bootloader, or in case of core boot, it's called payload, is loaded into memory, and that loads operating system. And I only care for the first stages as shown here. So, in a perfect world, for example, the core boot running on the ThinkPad X230, there are no BLOBs. Everything is open source. It has basically been reverse engineered, so some parts of it. But that also means there's no register documentation on some parts. That means you write magic numbers somewhere into the PCI space and then everything works. Which isn't that nice, but at least it's open source and you can see what it's actually doing. There's microcode which is loaded, as shown here, the yellow bar. It's loaded in an early boot block. It's not directly code, so I'm going to ignore it and claim it's 100% open source, even though it loads microcodes. And we have got another example here, core boot on a Supermicro server, X11 SSH. It uses multiple blobs. In this case, it's the firmware support package, FSP. And it occupies about 500 kilobytes of space in the SPI flash. And core boot itself, so the open source part of the firmware, only occupies 200 kilobytes. And core boot jumps into the FSP and let the FSP do all the hardware initialization. As you can see here, so one big part is in the ROM stage is bringing up the DRAM. And then in the RAM stage, it does all the device initialization. And sometimes core boots need to undo what FSP does because some features cannot be disabled. And then you have to, and there's also microcode updates. Again, it's loaded in early boot block. So, but I'm only concentrate again on the blobs. So what are blobs? Binary large object. There's no source code available for the blobs. Usually there's no documentation what it does, and that's because of that it's difficult to integrate into open source firmware. There might be security issues because you don't know which register is already locked or isn't locked, and you should lock it in open source firmware. There's no linker symbols. That means you always have to use the whole blob, even though you only need a single feature out of it. There's no garbage collection, and yeah, the size cannot be reduced. Also, debugging is quite difficult. Usually there's no debug output because that would increase the size, and I guess it would allow or give insights what the blob actually does. Okay, so what are we allowed to do? I'm from Germany, and this is from law translated into English. So I'm allowed to gain basic knowledge of the ideas and concepts by just loading, displaying, running, transmitting, saving the program, and I don't need permission from the copyright owner. That basically means I can do reverse engineering, and yeah, even though then there's some sentence in the license that doesn't allow it. Yeah?
The question is, what is the implication of basic in the German law?
Okay, yeah, so the law isn't very precise. Okay, yeah. So there's another passage. It talks about decompilation, and it says it's only allowed for interoperability, but it doesn't say what decompilation at all. So it just mentioned this term. And it also says if you decompile it, you're not allowed to create a program that does basically the same. So we cannot create a free and open source software out of it. Yeah, so the only thing we can legally do is black box testing. We observe, that's just shown here. So black box testing. We have the firmware that talks to the hardware, and we can observe the I/O. And we can observe BIOS options, like settings you usually do in the BIOS menu. And if we observe both, we can generate a model out of it. And that model can be free and open source. But there's some issues. It only works on a single hardware. It's very difficult to see branches inside the firmware and to catch corner cases. There might be some fix-up for specific devices, and if we don't have that device, we simply won't see that fix-up when we observe the I/O. Yeah, so our model is likely incomplete, and there's lots of data we need to analyze, and we cannot put the firmware in like emulator, like QEMU, because it doesn't emulate the hardware. Okay, so what do we need to do? We run it on real hardware, and there's similar projects like Serial Eyes and Avatar too, that put the firmware inside a patched QEMU, but that's something we haven't done. So we put the emulation inside the firmware. And in this case, it's a library called libx86emu. And it allows to trace I/O and send it over the serial port. And it also allows to upload BIOS option, like change it to fake I/O or skip I/O. And yeah, the whole thing is done in a client-server model. Let me explain. So this is an open source library. You can find it on GitHub. It emulates x86 CPUs. So AUTOREV currently only works on x86, but in theory it runs on any architecture. Yeah, so the library allows to hook into specific instructions, and in our case we only care for I/O instructions.
It only does 32-bit, doesn't it?
Sorry?
It only does 32-bit, right?
It only does 32-bit. Yes, that's right. And what we do, we never, so we don't jump to ROM stage. We continue running in ROM stage, and instead load the library, and the library emulates everything. And so the RAM stage and the payload run in this emulated environment. The stages doesn't even know that they're being emulated. Again, here you can see the blobs. And what we are doing is we're tracing all the I/O of the blobs in the RAM stage. So this method works on any hardware as long as there's a serial port. And with that, we can observe memory access, like read and write, access to the PCI config space, access to I/O ports, and machine-specific registers, and the CPU ID instruction. And so that's the complete set of I/O firmware talks to hardware, and we can just observe it with this library. You can see here it's not that readable, but you get an impression what it does. So in this case, it's mostly PCI reads, and the last two are memory accesses. What we actually can do is convert it to something more readable, like C code. You can compile it and run it on, or replace the blob and put it into your firmware, but it likely won't work, and it only works on this single machine for the single configuration, which is not what you likely want. So, what we can do is generate a syntax tree, and that's the main feature of the framework. It collects traces and put them into the database, and then merges all the traces into a syntax tree. As you can see, it's a directed graph, and if you have two runs, on the first run, the BIOS option 1 is set to true, on the second it's set to false, and you can see there's a slightly difference in the I/O operations, and we can then merge it into a graph and actually see which BIOS option triggers which pass in the tree. The merging is done with the LCS algorithm, and it tries to generate a minimal graph that has some issues, as it turned out. And we then can convert the abstract syntax tree to a high-level language again. We only implemented this for C, but in theory we could just generate anything like Go or Ada or whatever. Analyzing the mesh is quite time-consuming. Right now we only tested this with QMO and a small example, and in this case it's okay, but on real hardware it's pretty slow. You can see here that's the abstract syntax tree converted to C code. And this is another example. So the framework ships with a simple QMO core boot image that runs in QMO. As you can see, that's the graph generated. Every node is a single I/O instruction. If you generate C code out of it, it doesn't look that pretty. It's not even complete. It just continues below the slide. So that's only half of it. And that's something we need to work on and make pretty C code. There are quite a few to-dos. We would like to add plugin support, detect loops inside the firmware, because right now we can't. Detect read, modify, write operations. Usually only one bit is set or cleared. We can't detect that right now. There's no dead code detection, so if we run into a code path we shouldn't, and it just crashes, we won't see that. Yeah, we have no segfault reboot detection. We need to work on making pretty C code, yeah, and optimize the abstract syntax tree even more. Then there's usually the question, can we reverse engineer like the complete FSP and have some stats? So assume you have 4 CPU sockets with 4 CPU each and 4 DIMMs for memory, and you test 4 different DIMMs, 2 south bridges, 16 USB ports, quite a few PCI Express lanes, which can be again equipped with different devices, up to 8 serial ATA ports, and FSP has quite a lot of options that can be configured, and I only assume they can be true or false. Then we have 2 to the power of 588 times 15 minutes to collect a single trace, and yeah, that's going to take quite a while. And then after you collect all the traces, you still have to analyze the AppSec syntax tree and generate C code out of it. So black box testing might give insights into the firmware, into small parts of the firmware, but it's likely not the correct approach to reverse engineer a complete hardware initialization like the FSP. And that's it already. I think I was quite fast. Do you have any questions so far? Yes.
Have you taken timing into account as well? I remember things like DRAM setup especially.
Sorry? The time?
I remember that especially DRAM setup is very timing critical, where
Yeah.
you actually have to like token MIO and then wait for so many nanoseconds, which usually in code is even represented as like random operations or not. And then you just poke things again. So do you also record timing?
So the question was if I record timings. Right now, it doesn't record timings, and as you have seen, we only trace I/O in the RAM stage. So DRAM training isn't, or it isn't possible yet to capture DRAM training. Only everything that lives in the RAM stage. Yeah. As we send everything over the serial, the COM port, it takes a while, and we might run into some timing issues that bits are already set because we wrote out a single line over the serial. So yeah, we could work on that. Maybe use a different approach of sending the traces. Yeah.
Did you observe any behaviors that were obviously bugs?
So I only recorded one trace. Oh, sorry. Yeah. So the question was if I observed any bugs in blobs.
Yes.
Yeah. So I only run a single trace on a FSP. Yeah. That's why I said it takes 50 minutes. And I didn't have that much time to collect more traces. I continued working on the QMO demonstration because it takes about 5 seconds to capture a complete trace. Yeah, but yeah, that's something we could do. Just let it run like overnight and then analyze the C code.
To explain the question, we did an emulator for running DFI option ROMs, and there, when you run x86 for option ROM code in an emulator, you run into lots of like no pointer references and other things that you don't see when you run a data table. So you need to emulate something as well.
Yeah, yeah. So we are running blobs that are usually compiled into protected mode, so we won't see any issues with running option ROMs that are usually compiled into 16-bit real mode. I doubt that there will be lots of issues with it, because we can see that those blobs are working quite well on modern computers, and yeah. Yes, please.
It's good to see that you're trying to stay at the right side of the law, therefore all these paragraphs. On the other hand, the definition of a trace is a matter for interpretation. If you write an emulator that actually gives the trace for every instruction, it carries out. I would still consider this a trace. Others would consider it to be a debugging exercise. But in this regard, the rather wavy formulation of the law may work into your favors. Because I see we do not even recognize a single instruction. You just have branches where stuff executes differently. You don't know what's happening in between. You don't have fine-grained timing, even an idea how long it takes before two pieces of memory are being read or written. So finding out the heuristics just to spot loops will already be quite a bit of a challenge. There may be shortcuts there, and I would suggest to consider some of them.
Yeah. So I think it was the note. The note was about the German law, and it turns out that we are likely on the safe side of the law, because we really only capture the traces and don't use it as debugger to trace every single instruction. And it could be quite challenging to detect branches and tight loops on the target, because everything is slowed down and we only really see I/O and not the decision to send out the specific instruction, the I/O instruction. Any other questions? Okay, then that's it. Thank you for attending.